Okay, so let me first talk about a few, well, organizational things. I already explained to you how the class is being taught, that it's, so to say, classroom and Zoom hybrid. I will record it. You can ask a question here through Zoom, or you can ask a question from remote through Zoom as well. And this way, regardless where you are, everybody can hear or read your question. So this is that. Then let us go through another few things that I have prepared here. So I said already that the classes will be recorded and posted on YouTube. So you can ask questions while during the class, or you can also ask them after the class. You can do this either via Zoom, or you can do this in person. So after class, you can also, of course, ask questions by email. In addition to that, I would be available for office hours. I think we can just keep things flexible. And if you want to meet with me, either via Zoom or in person, then just set an appointment with me, and then we will meet and talk about the questions that you have. I will teach the class solely PowerPoint based. Part of the reason is that, well, if I use the board, then not everybody can see what I write. So therefore, I will strictly keep it PowerPoint. And if there's something additional to write, I won't write it on the board, but I will write it to my computer via the Zoom session. And this way also everything is being shared. So I will post the lecture notes after, or even actually before each class on CourseSite, so you have them actually available in advance. Okay. So if you want to, you can already print them in advance. You can already read through them in advance in order to prepare for the class. So I will use an optional textbook that I actually have written by myself. It's actually written around this course. So I've used this course actually as a template to write the textbook. Okay, therefore what's in the textbook exactly matches this class. So I published this textbook on an online platform. It's called LibreTexts. So this is actually a platform where professors can publish online textbooks, which are then available for free to the students. And that means not only to the students of the particular class, but any student can read any textbook. Okay, so therefore, not only my textbook is actually on that platform that you can read, there are also other inorganic chemistry textbooks on that platform that you can read. So if, for instance, you feel, well, what I wrote is maybe not quite enough for my understanding, you can maybe look up a few of the other textbooks in the respective chapters, and that may also be helpful for you. But bottom line, I think that the textbook that I wrote should actually be enough. So this textbook also contains the homework questions associated with this class. So I took the homework questions that I designed and basically incorporated them into this textbook. So therefore, you have also all the homework questions associated with this class available as part of this textbook. So I do not collect or grade homework, so I leave this up to you when and how much homework you actually want to do. So you have to manage basically your time by yourself. with regards to that. So also actually the answer keys to the questions in this textbook as well. So you always also have the answer to the respective questions. Yeah, special accommodations, if you have any, so please tell me that as soon as possible. If you need any special accommodations, then I will accommodate these as best as I can. All right. So we have a few exams. So there will be 3 midterm exams and 1 final exam. So the exams will all be held in person. Yeah. So for the exams, you really have to come to the classroom. Okay. So each midterm exam will count 20%. So that makes overall 60% of the course grade, and then there will be a final exam at the end of the semester, which will account for the other 40% of the course grade. So 1 midterm exam can be dropped. So your worst midterm exam can be dropped. Okay. So for instance, if you score in exam 1 50%, in exam 2 60%, in exam 3 70%, yeah, then I will automatically drop your worst exam, yeah, which will be in this case the first exam, yeah, and your other 2 exams will count 30% to the overall course grade, okay, instead of 20. And your final exam will still count the remaining 40. So this way, if you don't do well on one of the exams, you have the possibility to drop it. The same is actually when you miss an exam, then this missed exam will be your dropped exam. Yeah? But you can actually not miss more than 1 exam. All right. So the final exam will be all comprehensive, and all material will be weighed equally. So the point of the final exam is really to test whether you have achieved an overview over the entire course material, and whether you have stored the entire course material in your head at the point of the final exam. Yeah? So I really expect that you have comprehensive knowledge over the course material, but by the end of the course. So with regard to aids, I will allow a calculator, but not a periodic table. So this is an inorganic chemistry course. So the periodic table is the heart of inorganic chemistry. Therefore, for this course, you need to know your periodic table. I will also test the periodic table. I can tell you already that. So it's very important for me that you know the periodic table. So like I said already before, homework is voluntary, will not be graded, and the homework questions are available via the textbook, which I mentioned previously. Because you can drop 1 exam, there will be no makeup exams. If you miss a midterm, then that will be your dropped exam. All right. So these are the administrative things. So next, I wanted to give you a brief overview over what you can expect in this course in terms of course material. So basically, this course is structured into 2 parts. 1 part covers more introductory topics, which are important for inorganic coordination chemistry. And in the second part, then I will teach more advanced topics, which will be all about coordination chemistry itself. Okay, so what are the basic topics? So that's atomic structure. You have probably already heard about atomic structure in your a general chemistry course and then maybe other courses as well. I will review this. I will either present it in a compressed form, or I will go into more depth, so that beyond what you have already learned, you learn additional information about atomic structure. So the second topic will be symmetry and group theory. So symmetry and group theory are actually mathematical concepts, but they have a lot of application in chemistry, in inorganic chemistry, in organic chemistry, and also in coordination chemistry. And they are particularly useful for chemical bonding. And for that reason, I will teach a chapter about symmetry and group theory, and then the next chapter apply symmetry and group theory to chemical bonding, in particular to molecular orbital theory. So you've probably already heard about molecular orbital theory as well, but in this course I will teach it in the context of symmetry and group theory, and the aim is to show you that with the help of symmetry and group theory, you can achieve a much better understanding of chemical bonding, and you will be able to construct molecular orbitals, far more easily in comparison to well, the traditional approach. Sorry about this. All right, then the last chapter will be about Lewis acid base and hard and soft acid base theories. So these two acid base theories are of particular importance for coordination chemistry. For that reason, I will give them a review here as well. In particular, I will present Lewis acid base theory from the perspective of molecular orbital theory, and then explain in which way hard and soft acid and base theory is actually a refinement of Lewis acid and base theory. And then later on in this course, we will apply Lewis acid and base theory as well as hard and soft acid and base theory to coordination chemistry. So these are the four introductory topics that I will cover. And then the second part, we will talk in more detail about inorganic coordination chemistry. So I will talk about nomenclature. I will talk about the structures coordination compounds can adopt. And I will discuss how we can describe bonding in coordination compounds. And in particular, I will discuss three types of bonding. We will cover the valence bond theory. We will cover a theory which is called crystal field theory. And then we'll cover a theory which is named ligand field theory. And you will learn about the advantages and disadvantages of each of these theories when applied to coordination chemistry. So after that, I will talk about electronic spectra, and that is because many coordination compounds have interesting optical properties. Many coordination compounds are actually colorful, and therefore it is important that you can explain these optical properties properly. And you will see that you can do this to some extent with crystal field theory and ligand field theory, but there are still questions that cannot be answered. And in order to answer these questions, then we have to introduce terms and term symbols. And with terms and term symbols, we can then get a much more detailed picture about the electronic spectra that can then explain the optical properties. All right. So after this, we will turn our attention to stability, reactions, and mechanisms. So the chemical bonding can explain why a compound is stable, how a certain compound reacts, and that is true for coordination chemistry as well. So we will see, well, what guides the stability, the reactions of coordination compounds, as well as the reaction mechanisms coordination compounds can undergo. So finally, I will give an introduction in a very important subset of coordination chemistry, which is organometallic chemistry. And here I will cover, well, two important classes of organometallic compounds in particular, namely metallocenes and carbonyls. And then you will hear about how these compounds can be applied in useful organometallic reactions. So many organometallic compounds are actually catalysts that are industrially widely used to make all kinds of chemicals, for instance, polymers, but also many simple organic molecules, acetic acid, for instance, one example. An example of a polymer which is produced by organometallic catalysis, for instance, polyethylene, of which we use many million tons. So while at the first glance, metallocenes and carbonyls may appear as kind of exotic molecules, they are surprisingly useful, and they are used in many ways in organometallic catalysis to produce organic molecules and organic polymers. Okay, so this is basically the outline of this course. So unless you have any questions at this point, we could actually start with the first chapter. So are there any questions right now? All right, then we can start with the first chapter, which is about atomic structure. So atomic structure, well, is based on what is called atomic theory. And atomic theory is basically an element theory, okay? So element theories have been out there for a long time. Actually, it goes back to the antique to explain the material world. So humans have realized, well, we are surrounded by a material world and we have matter appearing in many different forms. And how can we actually explain all the many forms matter can adopt? Okay. And from very early on, there was the idea that all matter is probably composed of, well, somewhat simpler matter, which is composed of something, well, even more simple. And basically that process would continue until you would have found, well, these forms of matter which are the simplest forms of matter, yeah, of which everything else is based on and by which everything else can be explained by. And these simple forms of matter we would call the elements, okay? And the ancient Greeks were actually the first ones who thought about this. And the first elemental theories were actually non-atomistic theories. So the first theories were one-element theories. So there was Thales, who thought of water as the only element, and there was Anaximenes, who thought air was the only element, and there was Heraclitus, who thought of fire as the only element. But as you can easily imagine, when you only assume one element, it's difficult to explain the complexity of all the matter by which we are surrounded. So therefore, then Empedocles thought, well, we can more easily explain the complexity of the material by assuming not only one element, but more than one. So that was the first multi-element theory. And he thought of fire, air, and water, which we already considered before, as well as soil as the four elements by which we could explain all the material world. Okay? You can easily see that these element theories are non-atomistic, okay? So they do not contain the idea that they are particles, which are not further divisible anymore, which is the central idea of atomic theory. But this idea was actually also introduced by the ancient Greeks, in particular by Leucippe and Democritus. Okay, so they had the first atomistic ideas, which means that when you take a piece of material, particle, then you can divide this particle into smaller particles, and these particles you can divide into even smaller particles, and so forth. But you cannot do this infinitely often. Okay, you can do this only a finite number of times until you have particles which are not further divisible. Okay, and these particles then would be called atoms, and a particular type of atom would constitute an element. Okay, so and with this ideas, of course, you could have many elements. Okay, you would think about many different kinds of indivisible particles, smallest indivisible particles. So this idea we basically still use today in atomic theory. Okay, so now we need to make a big jump in time. These ideas actually got forgotten for a long time until they only resurfaced about 2,000 years later with Dalton's atom hypothesis. Okay, so now let us understand how Dalton arrived at his atom hypothesis. And in order to understand this, we need to first, consider what were basically the origins of modern chemistry. And the father of modern chemistry is widely believed to be Antoine Lavoisier, who discovered the law of the conservation of mass, which paved the way of modern chemistry. So the law of the conservation of mass is now well established, but it's actually not obvious when you really think about it, because in many chemical processes, mass either seems to appear or it seems to disappear. So for instance, when you take wood, you can burn the wood, and after that you have maybe a little ash left, but other than that, it seems that your wood has disappeared. Yeah. While in other instances, mass seems to be created also. So the law of the conservation of mass was actually obscured mainly by the fact that it was not obvious that gases had a weight themselves. Yeah, that the atmosphere has a weight itself, and that gases have a weight itself. And that was only discovered after the vacuum pump was invented, because with the help of a vacuum pump, one could evacuate volumes of gas. It's not unwanted here. Flasks that contained the gas, and if you weight that flask, after you have evacuated it, it would weigh less than before. So that led to the idea that, gases and the atmosphere also have a weight, which in turn then led to the law of the conservation of mass, because one could take the weight of the gases now into account. All right. So the law of the conservation of mass, or discovery of the law of the conservation of mass, then led to the discovery of the law of the constant composition, also called the law of definite proportion. And this law was discovered by Joseph Proust. So now what does the law of the definite proportion state? It states that a chemical company, a chemical compound always contains exactly the same proportion of elements by mass. So the mass ratios of elements in compounds could not continuously vary. Okay, so there could only be certain fixed ratios. Okay, so for instance, carbon and oxygen make two compounds. That's carbon monoxide and carbon dioxide, as we know today. And of course, the mass ratio between carbon and oxygen in the two different compounds is fixed. Okay, it can be either ratio A or it can be ratio B, but it can't be anything else. There's nothing possible in between. So this is also not obvious, or was not obvious at the time, because it was not easy at this time to distinguish between pure compounds and mixtures. Right? So for instance, if you make a mixture of carbon monoxide and carbon dioxide, you can actually vary the ratio in that mixture continuously. And then, of course, you measure a continuous range of a carbon to oxygen mass ratio. Okay? So you need to very carefully make sure that the sample that you analyze is not a mixture, but it's actually a pure compound. But once you have ensured that you have a pure compound, then you would find the law of constant composition, also called the law of definite proportions. All right. So now John Dalton analyzed Proust's law in more detail, and he found that if two elements form more than one compound between them, okay, like carbon and oxygen, for instance, then the ratio of the masses of the second element, which would be in this example the oxygen, which combine with the fixed mass of first element, that would be in our example the carbon, will be the ratios of small whole numbers. Okay? So this was called the law of the multiple proportions because integer numbers appeared. Okay? And the law of the multiple proportions again seem to hold universally for all, well, compounds under investigation. So let us do one detailed calculation with this. So let us stick with the example of carbon and oxygen. So when you do element analysis of pure compounds that can form with carbon and oxygen, then you find that the first compound contains 42.9% by mass carbon and 57.1% by mass oxygen. And the second compound would contain 27.3% by mass carbon and 72.7% by mass oxygen. So now, based on that element analysis, can we show that the data is consistent with the law of the multiple proportions? Okay, you can do a fairly simple calculation in order to show this, and this calculation works the following way. So when we have 100-gram sample, then in the first compound, we would have 57.1 gram oxygen and 42.9 grams of carbon. Okay, because 57.1% of 100 gram gives 57.1 gram, and 42.9% of 100 grams, well, that's 42.9 grams of carbon. So now we have to calculate the mass of oxygen per gram of carbon. Okay, the mass of the second element per gram of the first element. So in this case, this is just 57.1 grams over 42.9 grams. Yeah? And that is 1.33 grams of oxygen per gram of carbon. Okay, now let's do the same calculation for the second compound. So if we can assume that we have 100 grams of our second compound, then this would mean that we would have 72.7 grams of oxygen and 72.3 grams of carbon. So what is now the mass of oxygen per gram carbon in this compound? So you see this is the following. It's 72.7 grams of oxygen over 27.3 grams of carbon, which is 2.66 grams of oxygen per gram of carbon. So now how does the law of the multiple proportions show through here? You can see it when you just divide 2.66 by 1.33, okay? And you will see that this ratio is the ratio of small integer numbers. So in this case, the integer numbers are 2 and 1 respectively. Okay, if you analyze different compounds with different elements, you may find, of course, other ratios, but the ratios would always the ratios of integer numbers, small integer numbers. So this is what the law of the multiple proportion states. So now the question is, of course, what explains the law of the multiple proportion? And Dalton said, well, we can explain these integer numbers by assuming atoms, okay? Particles that, well, are the smallest entities of a particular chemical element that cannot be divided any further, okay? So particles necessarily come in integer quantities, and therefore if you combine different atoms, you can only to make compounds, you can only combine them in integer ratios, okay? And that's the explanation of the law of the multiple proportion. All right, so here's just a very brief illustration of this principle. You can combine different atoms of different elements in the ratio of 1 to 1, 1 to 2, 1 to 3, 1 to 4, for instance. Okay, but you can, of course, also think of other ratios like 2 to 1, 2 to 2, or 2 to 3. And of course, there are many other possibilities. All right, so now Dalton also was already introducing atom symbols for the different elements, and you see some of them here. So for instance, the circle with a dot was symbolizing hydrogen. The simple circle would symbolize oxygen. So this symbol here would be the symbol for nitrogen, and that black dot here would be carbon. So of course, today we're using different atom symbols, but you see the principle is the same. So we also introduced the idea of combining the symbols of different atoms in order to assign this a structure of compounds made of more than one element. And you see here a few examples. So here you see the carbon monoxide, for instance. And you see the carbon monoxide would be, well, a combination of an oxygen with a carbon, and the carbon dioxide would be a combination of 2 oxygens and 1 carbon. Okay, you see that here the ratio of atoms is correctly predicted. You see, however, this is not always the case. So when you go, for instance, to the water here, you can see that Dalton thought, well, water is made of one oxygen and one hydrogen. We know today, well, we have two hydrogens and one oxygen in a water molecule. So can you imagine why this may be? So the reason is that in the carbon-oxygen system, there were already two different compounds known. Okay, so one could determine, well, the relative mass ratios of oxygen to carbon. But in the case of the hydrogen-oxygen system, there was only one compound known, so there was no other reference point to compare. Okay, therefore, well, Dalton just assumed, well, the most simple composition of one hydrogen, one oxygen. So if he had known hydrogen peroxide, for instance, already at that time, yeah, he would have probably predicted the formula for water correctly, because in hydrogen peroxide, really the ratio between hydrogen to oxygen is 1:1. And he would have found that in water, well, the amount of hydrogen is double in comparison to the water. Okay. So at Dalton's time, atoms really were believed to be indivisible, but we know today that this is not really the case. So atoms are the smallest particles that give, well, an element its chemical identity, but we know today that atoms are composed of subatomic particles, in particular protons, neutrons, and electrons. However, those don't have a chemical identity anymore. Okay, so the first subatomic particle which was discovered was the electron. It was discovered in the context of an experimentally observed phenomenon that needed an explanation. In particular, the phenomenon of, well, what was called cathode rays. So you see actually this principle here. So you have a tube, an evacuated tube, to which a high voltage is applied, yeah, and if the voltage was just high enough, then you would actually see mysterious rays that seem to go from the negative end to the positive end. And the question was, well, what are these rays? And Joseph Thomson experimented with these rays, and he found that they are being deflected by electric and magnetic fields. Okay, so for instance, when he applied here an electric field perpendicular to that ray, and, well, the positive pole was here at the top and the negative pole was here at the bottom, well, he found that, well, that beam was deflected toward the positive pole, and upon reversal of the polarity, well, the ray would bend to the other side. So he basically draw two conclusions from that. So firstly, these particles that would move, so that there are particles that move through the tube, and these particles would have a negative charge. Okay, that's why they are attracted to the positive pole. Okay, and secondly, these particles would need to have a mass. This is Why? Because of the principle of inertia, they are only deflected to a certain degree from their path. Okay, whereby of course the angle would depend on how strong the electric field here is. Okay, so from these experiments, he was able to determine a charge to mass ratio for these particles, and the numbers being here, and he named these particles electrons. Okay, so Thomson only determined mass to charge ratio. Only after him, Robert Millikan actually determined through an oil drop experiment, which I'm not going to explain here in more detail. You've probably heard this also in general chemistry classes, what the actual charge of an electron is and what the actual mass of an electron is. And you see here the two values, and of course these values are extremely small, so the charge is minus 1.6 times 10 to the minus 19 coulombs, and the mass is 9.1 times 10 to the minus 28 grams. So now, based on these results, Thomson also developed a first atom model which contained subatomic particles, and this is called the Thomson atom model. This is, of course, far different from state-of-the-art knowledge, but nonetheless, it has historical value in the sense that it, for the first time, introduced the idea that an atom is built up of subatomic particles. So what Thomson assumed here was that, well, an atom is kind of a spherical entity in which we have a positively charged mass, and well, the mass and the positive charge is homogeneously spread out within the atom. And then there would be electrons, which would be much lighter, would have the negative charge, and they would be embedded like raisins in a cake. Okay, of course that atom model would need to be experimentally tested and verified, and eventually this model proved to be not correct. Ernest Rutherford actually disproved this model by his famous gold foil experiment, upon which then the planetary atom model was developed. But I see our time is almost over, so I think we can start at this point, and we can